Hello everyone, and welcome back to the AI Research Roundup. I'm your host Alex. It's May 5th, 2025. Today we're diving into this ICLR conference paper published just over 3 months ago. Unlocking state tracking in linear RNNs through negative eigenvalues. It looks at linear RNNs efficient sequence models and why they often fail at state tracking tasks like parity. The key insight? Their state transition eigenvalues, controlling memory updates, are usually limited to positive values. This paper proposes extending that range to include negative ones. Okay, the first figure really highlights this core idea. It shows scaled accuracy on the parity task over training steps. The blue line, that's the standard LRNN, with eigenvalues limited to positive values between 0 and 1. It completely fails, stuck near 0. In stark contrast, the orange line, representing the extended -1 range, rapidly achieves perfect accuracy. It's a pretty dramatic difference, especially for these diagonal models. Building on that, this figure gives a great visual intuition for why parity fails with standard LRNNs. Okay, so with only positive eigenvalues, the internal state either converges or diverges monotonically. It can't really flip-flop effectively over time. But look at the middle plot. When you allow a negative eigenvalue, say -1, the state clearly alternates between two distinct regions. This perfectly mimics the even and odd states required by the parity automaton shown on the right. Okay, so figure 3 provides a concrete example of how these state tracking operations, like permutations, can be built up. It shows a permutation of 3 elements, broken down into a sequence of 2 swaps. Each swap corresponds to multiplying by a specific matrix. Here, they're using these generalized householder matrices. This ties back to the theory, suggesting that by allowing negative eigenvalues in these matrices, the LRNN can actually represent these complex, group-based operations needed for state tracking. Okay, moving to the experimental results. Table 3 really puts this theory to the test. It compares different models on formal language tasks, like parity and modular arithmetic. Look at Mamba and DeltaNet. With the standard 0, 1 eigenvalues, they fail parity, just as predicted. But extending the range to -1, one gets them perfect scores. And on modular arithmetic, especially without brackets, DeltaNet -1, one jumps way up, much more than Mamba, showing that non-diagonal structure really benefits. Right, so after seeing those performance gains in Table 3, you might wonder how exactly they achieved that extended eigenvalue range. Well, Table 2 here summarizes the specific mathematical changes. For the diagonal Mamba model, they adjust the state matrix to diag 2's -1, and for DeltaNet, with its non-diagonal structure, it becomes I minus 2 times beta kk transpose. These are the concrete modifications allowing that critical -1 to 1 range. Alright, following those implementation details from Table 2, Figure 4 shows the impact on sequence accuracy for S5 group tasks, which involve permutations. Across several variations, the pattern is clear. DeltaNet, with the extended -1 eigenvalue range, even with just 1 layer, achieves near-perfect accuracy far beyond the training sequence length. Mamba also improves, but DeltaNet's non-diagonal structure really shows its strength on these complex, state-tracking, permutation-based problems. So, bringing it all together after seeing those S5 results, the main takeaway is pretty clear. Extending the state matrix eigenvalues to that -1 to 1 range, well, it's crucial for unlocking state tracking in these LRNNs. Tasks like parity, modular arithmetic, permutations, they become solvable. And we saw DeltaNet, with its non-diagonal structure, really benefit most. Importantly, this happens without hurting stability or efficiency. That's our roundup for today. Thanks for joining.